A cube has 8 vertices, 12 edges, and 6 faces. But hidden inside the cube is another configuration that is much smaller, much stranger, and potentially much more algebraically expressive. Take the 4 body diagonals of the cube. Each diagonal joins a vertex to its antipodal vertex, and all 4 diagonals meet at the center. At first, this looks like an ordinary arrangement of 4 intersecting lines. But suppose that the intersection at the center is not treated as a single ordinary point. Suppose instead that we resolve it into a structured geometric object. The resulting object is what I will call the Fano Seed. The Fano Seed has 3 interacting components: a collection of 4 orbifold sheets, a 3-colored seam locus, and a finite non-commutative symmetry group. These components naturally divide into 4 geometric objects and 3 seam directions. 4 plus 3 equals 7. That number is not decorative. It is the first indication that the geometry is organized by the same incidence pattern that appears in the Fano plane. Let V3 be the set of 8 vertices of a 3-dimensional cube, all sign vectors with entries plus or minus 1. The antipodal involution sends each vertex b to its negative minus b. Taking the quotient by this involution gives the set a 3. Since the 8 vertices form 4 antipodal pairs, a 3 has exactly 4 elements. Each antipodal pair determines 1 body diagonal of the cube. These 4 pairs will become the 4 geometric sheets of the seed. The cube is therefore not the seed itself. It is the combinatorial scaffold from which the seed is constructed. The vertices tell us where the distinguished cone points lie. The antipodal pairing tells us which cone points belong to the same sheet. And the common intersection of the 4 body diagonals tells us where the sheets must interact. Instead of representing each antipodal pair by a 1-dimensional diagonal, we replace that diagonal by a 2-dimensional orbifold sheet. For each antipodal pair alpha, let sigma alpha be a compact football orbifold. Topologically, a football orbifold is a sphere with 2 distinguished orbifold cone points. The 2 cone points of sigma alpha are placed at the 2 cube vertices belonging to the antipodal pair alpha. The notation S2 of M alpha and alpha means that the sheet is a 2-sphere equipped with cone points of orders M alpha and N alpha. For the basic symmetric model, one may take the 2 cone orders to agree, although the general construction does not require this. The disjoint collection of sheets is the disjoint union of the 4 sheets sigma alpha. But the 4 sheets are not supposed to remain disjoint. They must be sewn together. In the unresolved cubical picture, all 4 body diagonals pass through the same central point. If we simply identify the 4 sheets at one point, we lose almost all information about how one sheet passes into another. So instead of retaining a single central point, we replace it by a seam graph, gamma. The seam graph records the allowed transitions among the 4 sheets. The space I is obtained by gluing the 4 orbifold sheets along prescribed seam strata. The equivalence relation means that the identifications are controlled by the graph gamma. This distinction is essential. The seam graph is not the collection of cone points. The cone points remain at the 8 vertices of the cubical scaffold. The graph gamma is the internal interface along which the sheets are sewn. Thus, the geometry has 3 visibly different strata. First, the regular interiors of the 4 sheets. Second, the internal seam locus gamma. And third, the 8 cone points at the ends of the sheets. The seed is therefore not a manifold in the ordinary sense. It is a compact, stratified, seamed orbifold space. Now we reach the reason for the name Fano Seed. The geometry naturally contains 7 basic types of data. There are 4 sheet colors: sigma 1, sigma 2, sigma 3, and sigma 4. There are also 3 seam colors: gamma red, gamma green, and gamma blue. So the seed carries a decomposition 4 plus 3 equals 7. 7-element incidence structures immediately suggest the Fano plane, the smallest finite projective plane. The Fano plane has 7 points and 7 lines, with 3 points on every line and 3 lines through every point. It also encodes the multiplication pattern of the 7 imaginary units of the octonions. In the Fano seed, the analogy is not that each sheet literally equals a point of the classical Fano plane. Instead, the 7 colored components participate in a Fano-type incidence algebra. At the level of types, the basic rules are seam times seam gives seam, sheet times sheet gives seam, and seam times sheet gives sheet. These three rules express the geometry of interaction. Two sheets intersect through a seam. A seam acts on a sheet by transporting, twisting, or re-identifying it. And seams compose with seams to produce further seam transformations. This is the geometric shadow of a 7-part non-commutative incidence system. One possible labeling is to assign the 7 components to the 7 non-zero vectors of the vector space F2 cubed. For example, the 3 seam colors correspond to the 3 standard basis vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. And the 4 sheets are assigned to the remaining vectors 1, 1, 0, 1, 0, 1, 0, 1, 1, and 1, 1, 1. The lines of a Fano plane are the triples x, y, and x plus y, where addition is performed in F2 cubed. This gives a precise combinatorial mechanism for determining which triples of colors are incident. For example, 1, 0, 0 plus 0, 1, 0 equals 1, 1, 0, so one Fano line contains gamma red, gamma green, and sigma 1. Likewise, 1, 0, 0 plus 0, 0, 1 equals 1, 0, 1, giving the line gamma red, gamma blue, sigma 2. And 0, 1, 0 plus 0, 0, 1 equals 0, 1, 1, giving gamma green, gamma blue, sigma 3. The remaining 4 Fano lines describe the interactions involving sigma 4 and pairwise combinations of the other sheets. This finite labeling does not by itself determine the full geometry, but it supplies a compact incidence skeleton for the seam gluing rules. The number 7 also appears topologically. For the classical 3-dimensional seed, the seam graph may be chosen so that its first Betti number equals 7. For a connected finite graph, the first Betti number equals the number of edges minus the number of vertices plus 1. So a first Betti number of 7 means that the seam graph contains 7 independent one-dimensional cycles. This is not merely a numerological repetition of the Fano number. The 7 cycles provide 7 independent winding channels inside the seam locus. A function path or dynamical state on the seed can travel through these channels, acquire holonomy, and return transformed. The Fano incidence structure therefore has both a combinatorial interpretation and a topological carrier. The third component of the seed is its symmetry group pi. This is a finite, generally non-commutative group acting on the seamed orbifold space. The action must preserve the complete structure, the orbifold data, the seam incidence, the color rules, and the allowed sheet identifications. Here, the target denotes the group of piecewise dianalytic orbifold automorphisms preserving the seam structure. In a cubically symmetric model, one can choose 3 quarter-turn generators pi x, pi y, and pi z, each of order 4. But these generators do not generally commute. The order in which the seed is rotated matters. A quarter turn around the x-axis followed by a quarter turn around the y-axis need not produce the same sheet arrangement as performing those operations in the reverse order. This non-commutativity is fundamental. The seed is not merely a static glued space. It is a finite geometric register whose states are related by a non-commutative action. One concrete model for pi is supplied by the rotational state system of the 2x2x2 Rubik's cube, also called the pocket cube. This model provides exactly the kind of finite non-commutative quarter-turn dynamics needed by the seed. The cube is not being introduced merely as a puzzle. Its move group gives a practical representation of how local rotations can permute the sheets and seams while preserving a global incidence law. In this interpretation, a state of the pocket cube corresponds to a particular arrangement of the seed data. A move does not destroy the seed. It transports the seed to another admissible state. The group orbit of the seed therefore records every configuration reachable from the original seed by the allowed finite motions. The central philosophical move is to reinterpret the entire Fano seed as a generalized point. An ordinary point has no visible internal structure. The Fano seed does. It contains 4 two-dimensional orbifold sheets, a 7-cycle seam system, 8 cone-point ports, and a finite non-commutative symmetry group. Yet from a sufficiently large scale, the entire object can still be treated as one localized unit. This suggests a new kind of geometry. Instead of constructing a space from featureless points, we construct it from points that already carry topology, orbifold structure, incidence data, and internal symmetries. The resulting ambient geometry would not merely specify where a point is. It would also specify what kind of internal state that point occupies. Suppose we plant the seed at the origin of Euclidean space. The origin is no longer an ordinary featureless point. It now carries an internal pi state. Acting on seed changes the way its 4 sheets and 3 seam directions are arranged. If the surrounding geometry is coupled to that internal arrangement, then a group action can induce a deformation of the local ambient space. This does not yet constitute a physical theory or a fully defined geometric field equation. It is a program. The mathematical task is to specify a coupling rule which tells us how a change in the internal seed state modifies the surrounding geometry. One possibility is that different sheet permutations determine different local metrics. Another is that seam holonomy determines a connection. A third is that the group orbit determines a finite family of admissible local geometries. The Fano Seed brings several kinds of mathematics into a single finite object. It combines cubical combinatorics through antipodal vertex pairs, orbifold geometry through the 4 football sheets, graph topology through the seam locus, finite geometry through Fano plane incidence, non-commutative algebra through the group pi, holonomy through cycles in the seam graph, and spectral analysis through functions propagating across the glued strata. The significance of the construction is not that these subjects have never interacted before. They have. The new proposal is that they should be packaged into one elementary geometric unit and treated as a replacement for the classical point. The Fano Seed is the 3-dimensional member of a larger spectral tower. For an n-cube, let Vn be the vertex set, and let An be the set of antipodal pairs. Then the number of antipodal pairs is 2 to the power n-1. At level n, one assigns a compact n-1 dimensional orbifold sheet to every antipodal pair. These sheets are glued along a stratified seam locus, gamma n, and a finite group pi n acts by structure-preserving automorphisms. At level 0, the seed reduces to the classical point. At level 1, the scaffold is a line segment. At level 2, the geometry begins to develop multiple arcs and seam points. At level 3, the full Fano organization appears: 4 sheets, 3 seam colors, and 7 independent seam channels. Thus the Fano Seed is not an isolated object. It is the first level at which the tower acquires a genuinely rich, non-commutative internal geometry. It is important to distinguish the parts of this construction that can be defined immediately from the parts that remain conjectural. The cubical scaffold, the antipodal pairing, the orbifold sheets, the seam gluing, the Fano labeling, and the finite group action can all be stated as precise mathematical data. What remains open is the deeper theory built from that data. Among the central questions are the following: which seam graphs produce the most natural Fano incidence? Which orbifold metrics are compatible with the full group action? Is there a canonical algebra associated to the 7 colored components? Can functions on the seed produce useful spectral or automorphic invariants? How should a seed-valued point deform the space in which it is planted? And what geometric category contains the inverse limit of the entire seed tower? These are not solved consequences of the definition. They are the research program generated by it. The Fano Seed begins with a simple observation. A cube has 4 antipodal body diagonals. But when those diagonals are resolved into orbifold sheets and their central intersection is replaced by a structured seam graph, the cube reveals a 7-part internal geometry. 4 sheets, 3 seam directions, a Fano incidence law, a 7-cycle topological register, and a finite non-commutative group acting through quarter turns. The proposal is to regard this entire configuration as one enriched point. A point with internal topology. A point with memory. A point with non-commutative states. A point that can be planted into a larger space and allowed to act on the geometry around it. The classical point tells us only where we are. The Fano Seed may also tell us what transformations are possible there.